Hi everyone, I'm Stephanie and today I'll be going over some lab math problems that you will encounter throughout the rest of the semester. So first, I'll go over some simple stock solution problems. So here at the side, it gives you a bit of background information, basically letting you know that 1 molar solution is a solution in which 1 mole of a compound is dissolved in a total volume of 1 liter. Now, how you know what 1 mole of a compound is if it were in the periodic table, you'll see it there, but usually compounds are a mixture of them. So whenever you're working in the lab, it'll usually say it on the original container. And from there is where you can do your different calculations. Whenever you're doing lab math problems in the lab, for example, in class or later in the future, if it's a problem, it'll always let you know what the molecular weight is. So, for example, here, molecular weight of 5844 for sodium chloride means if you want a 1 molar solution, you get 58.44 grams of sodium chloride, and then you add water up to the 1 liter mark. Whenever you're making solutions, you always want to weigh the compound first and then add whatever liquid you're meant to up to the line. You never want to just add that difference beforehand. So here to the side, we have another example to get us started. So how much arginine do you need to make 0.1 molar or 0.01 molar solution of arginine? And then here it gives us its molecular weight. So for this, you can just write down the information we know. So the molecular weight, so we know that it's 174.20 grams of it is in 1 molar of the solution. So what we want is 0.01 molar. So if we were actually to just go ahead and do that division, we can see how many fold of that solution is. So here, that would actually result in 100. So we know it's a 100-fold solution that we're making, or dilution, I should say. So one way to do this would actually be to simply divide 174.20 grams by 100, and that lets us know that we need 1.742 grams of arginine for the solution, and then we would just fill it to the 1 liter mark. So now we can go to the next one, which would be making stock solutions. Here, concentrations, weight divided by volume as a percentage. So here it gives you a bit of background on how it is done. This is a bit rare to see, but you will still see it around. So it is always important to know how to approach problems whenever you come across them. So here it gives you a sample problem, but I think it's always best to work them out and learn that way. So here the problem is, how much sodium chloride do you need to weigh out to make 1 liter of a 0.9% sodium chloride solution? So here, just always start off with what you know. So first, what it's asking? It's asking how much sodium chloride do you need? So that means is it'll probably be in grams. So you can start with that being your X or unknown variable, and you need 1 liter. So I will go ahead and I'll just convert that into milliliters, so 1,000 milliliters. And we know that is what this concentration would be. So, however, it's a percentage, so we need to multiply that by 100. And then we have, this is our final setup problem. Now we actually just have to solve it. So here it's just simple arithmetic math. So we have this 100 that's being multiplied, and we want to get the X by itself. So we can just go ahead and divide that 100 off of both sides. But then we have this 1,000 here too that's being divided. So we're actually going to go ahead and multiply that over. And it's looking a little crazy now, but I just go ahead and multiply that all out, and then we have our unknown of X number of grams to, it comes out to 9 grams. And you can just also figure that out by trying to cancel out the zeros and moving a place over. But we have 9 grams of sodium chloride. But of course, the question is saying you want to make 1 liter sodium chloride solution. So how you do that is then you weigh this out, add it to your container of choice, and then you fill that container to 1 liter with water or whatever other diluent you are using. Now we are off to dilute a solution to an unspecified final volume in just 1 step. So that seems pretty specific, but as we go on, you'll see how many different types of problems there are. So for example here, it's asking us to dilute a solution that has an initial concentration of solute of 10% down to 2%. So here we see if we're going 10% to 2%, one way to do this is to go ahead and take 1 volume of 10% solution, and then we have 4 volumes of our diluent. So this is traditionally water, but of course it depends for the solution that you're making. So we're just going to be broad here and say diluent, and that gives you a total of 5 volumes of your 2% solution. Now we're just saying volumes because we're being very broad here, but of course you can change these with whatever unit as long as it's consistent. So we can say 1 milliliter of 10% and 4 milliliters of the diluent is 5 milliliters of 2%. You can make it liters, you can make it whatever you want as long as they stay consistent. So this is one way to say that, and of course that's why it's an unspecified final volume. We're just working with ratios at this point. Now it is important to note, so this here would have been a 1 to 5 dilution. Now a common mistake that people make is, let's say when they're halving the dilution, or let's say you're going from a 1 molar to a 0.5 molar, a lot of people will refer to that as a 1-to-1 dilution mistakenly. That is not correct. A 1-to-1 dilution is an undiluted substance. A way to think about this is this first number. So of course, if we're doing like a 1-to-2 dilution instead, this first number is whatever the stock solution is, or whatever your main sample that you want to dilute. And then this is, the second number is your total volumes. So if you think about it, let's say you have a sodium chloride solution, like a stock solution, and it's a 1 molar solution, you want to make it into 0.5 molar, then this would be that. So you have 1 volume of a stock solution, then you have 1 volume of your diluent for a total of 2 volumes. So if it's a 1-to-1 solution, you can think of it as 1 part stock out of a total of 1 volumes, hence it's undiluted. So that is something students mix up every year without fail. So just make sure you understand that a 1-to-1 is not the same as a 1-to-2. A 1-to-1 isn't a dilution, it's just an original. A 1-to-2 is actually that 50% dilution. Perfect, now we can move on to dilute a solution to a specified final volume in just 1 step. So here it's telling you, for example, prepare 100 milliliters of 10% alcohol from 95% alcohol. Now, this here, if you look over, is the most important formula we will encounter throughout this whole lab math module. Honestly, I guess it's technically the only formula, but with most of the problems that we did previously, we could have used this formula, and it's actually more intuitive to use this formula in problems like that. So here, oh, and this is just talking, here you can see first concentration, first volume, second concentration, second volume. So here, prepare 100 milliliters of 10% alcohol from 95% alcohol. So these here are together. And then this one is what we don't know. So we don't know how many milliliters we need in order to make this. So that's how you always want to split it up, making sure what numbers are in what, like, go together in that equation. So here we can start. So we want to make 95% alcohol, and we don't know how many milliliters we need to make that, but we know that this is what we have, but we know we want to make 100 milliliters of alcohol at a 10% concentration. And it doesn't matter which one you put first, it's equivalent. So if I had put this part of the equation over here and made that equal to each other, it doesn't matter. But anyway, now it's simple math. We can just go ahead and divide this by 95%. Obviously, these cancel out. We're left with milliliters. The units match. That's always good. That's always necessary, really. But this leads us with 10.5 milliliters of our original stock solution. So in order to actually prepare the 100, you would use the 10.5 milliliters of 95% alcohol, and then add diluent, or in this case it would be water, up to the 100 milliliter mark. So but of course you only do this after you've already added this step. Okay, so now I'll go ahead and show you guys how to dilute a solution to an unspecified final volume in several steps. In this example here, it's letting us know you have a stock solution of protein containing 10 grams per milliliter. You want a concentration of 2 milligrams per milliliter. How would you perform this dilution in just 3 steps? Okay, first let's write down what we know. So here it's telling us we have a stock solution of 10 grams per milliliter, and we want to go ahead and turn that into 2 milligrams per milliliter. An alarm should start ringing in your head that we have 2 different units. So before we move on, we want to make sure that those units match. You can either turn the grams into milligrams or the milligrams into grams. Since we'll be dealing with a lot of decimals, if we change milligrams to grams, I'll just go ahead and do the opposite. So change this 10 grams into 10,000 milligrams per milliliter. We know that we want to change that to 2 milligrams per milliliter. In order to do a dilution factor, you just go ahead and divide the 2. So 10,000 divided by 2 leaves us with a dilution factor of 5,000. Now it is saying to perform this dilution in 3 steps. So we just go ahead and split this dilution factor up. You can do this several ways. The way I'm just going to do it intuitively, it's telling me to do a 1 to 50, a 1 to 10, and a 1 to 10. Whenever you go ahead and check to make sure that you have the right dilution factor, you just go ahead and multiply these guys together. So 50 times 10, 500, 500 times 10, 5,000. So we know we did these right. So, and I usually like to do the bigger dilution first. So instead of doing a 1 to 10, 1 to 10, 1 to 50, I usually just like doing the bigger one first, just because that means I'll be dealing with bigger volumes, and bigger volumes will be more accurate than trying to deal with way smaller volumes. It gives more room in that sense. So now from here, it's just a matter of how will we actually be performing this. Now we know what the different dilution steps are, but let's see. So we have 10,000 milligrams per milliliter, and we want to do a 1 to 50 dilution. So one way to do this is we just go ahead and grab 1 milliliter of this solution. So 1 milliliter of our 10,000 milligrams per milliliter solution. And then we're going to add 49 milliliters of our diluent. And that leads us to, and again, that is just a 1 to 50. So you can just go ahead and divide this number by 50 to give you your total or your final dilution for this step. And that comes out to 200 milligrams per milliliter. Now we want to do the same, but just with this second one. So we can do 1 milliliter of this 200 milligrams per milliliter solution, and then we can just go ahead and add 9 milliliters of our diluent, and that would result in a 20 milligram per milliliter solution. Then we can just do our last one, same as the one from above, 1 milliliter of our now 20 milligrams per milliliter solution, plus 9 milliliters of diluent, leaves us with our final 2 milligrams per milliliter solution that we wanted. Now here, the reason we were able to do it this way too is because it didn't tell us how much it wanted as a final volume, which is why we could do it this step. If it did tell us a final volume, we would just go ahead and do it with the M1C1 or M1V1, M2V2 method as we did here. But let me see if that is all done there. And then just one final note. Here I went ahead and noted the actual milliliters of diluent that we'd be using. However, in the lab, if you were actually doing this using, let's say, something like a graduated cylinder to measure these when dealing with bigger volumes such as these, we would actually be filling it up to that line like before. So we would add 1 mil and then fill it up to the 50 mil line. Just good practice, so on and so forth. But when dealing with smaller volumes that we'd have to use micropipettes, that's when we would just go ahead and actually do the difference like this. And now we will go over how to dilute a solution to a specified final volume in several steps, as opposed to the last problem where it was an unspecified final volume. So for example here, it says you want a 1 to 3,000 dilution of serum and you need 2 milliliters. How would you perform this dilution in several steps? So again, we just look at our big dilution factor, 1 to 3,000, and you need 2 mils. You could go ahead and start splitting this up. Yet again, you can just start trying to do that intuitively. So 3,000, never see that. I think, let's say, doing a 1 to 30. A 1 to 10, that leaves me to 1 to 300. Then if I do another 1 to 10, that gets me to that 3,000. Yet again, this is just a matter of practice. While doing a lot of problems, you'll pick up different patterns and just intuitively make sense. You don't want to split them up too much because then obviously you're adding more work to yourself and honestly more room for error as well. But you don't want to make them so small that the volumes you're dealing with are very large. So I think 3 is always good. Obviously depends on the total dilution factor, but here a 1 to 30, 1 to 10, 1 to 10, all of them seem very reasonable to me. So go ahead and do that. And now you need 2 milliliters. How will you perform this dilution? Okay, so in order to do this, I can just go ahead and first do the 1 to 30. And I can just go ahead and actually deal with milliliters in here. So I can go ahead and do 1 milliliter of serum and then 29 milliliters of my diluent. Leaves me to that 1 to 30. Then I can go ahead and take this 1 to 30 solution and use 1 milliliter of the 1 to 30 solution. Add 9 milliliters of my diluent, and then that leaves me with a, this here was a 1 to 10, but a total of a 1 to 300 solution. And then I'll just go ahead and get 1 milliliter of the 1 to 300 solution and add 9 milliliters of my diluent, and that's leaving me with my final 1 to 3000 solution. As you can tell, it actually leaves me with 10 milliliters of solution. Now, it's okay when you're doing lab problems like this to have some extra volume, since, for example, if I were to calculate to make exactly 2 milliliters, there could be a lot of room for error in that sense. So splitting it up this way is good whenever you're just doing broad experiments, eating a little more, a little less. It's always good to have that accounted for. However, yet again, if I wanted to go ahead and do it to a very specific volume, I also could have done that. It's just a lot more finicky that way. Or I could have yet again gone back to the C1, V1, C2, B2. Honestly, this is what you always end up going back to. But yet again, for a problem like this, this is usually the step that they want you to go through. So very similar to the last. Now we can talk about some serial dilutions. This one here is a problem you'll see quite a lot, especially in the microbiology lab. So here it's asking you how many bacteria were present in the original sample in CFU per mil. CFU is colony forming units per milliliter of the sample. So here what was done was different dilutions were plated, and that resulted in different number of colonies counted. What you need to know whenever you're dealing with number of colonies is the countable range. There is a countable range of 30 to 300. Anything more, so anything above 300 is deemed too numerous to count. Anything below 30 is deemed too few to count. So this is the golden range. You're basically going to disregard everything outside of this range. So here we see that there's actually two different dilutions that fall within this range. There is the 10 to the negative 2 and 10 to the negative 3, 241 and 35 respectively. So these are the ones that we're going to look at. These, not so much. Now, something to always keep in mind, however, is when your dilutions get very low, sometimes you'll encounter dilutions that don't really make sense. Let's say this was 35, and then here you might get like 9, and then at the next one you might get like 12. And you're thinking, how can that be if my dilution is getting lower and lower? Whenever such a small dilution, or let's say a control sample, has number of colonies that are unexpected or too high, a possibility is that the sample is contaminated. So you also always want to make sure that, for example, here, if there had been like a control, to make sure that doesn't really have any number of colonies, to ensure that the sample hasn't been contaminated. But I digress. So going back to the original question of how many bacteria were present in the original sample, yet again, I want to go ahead and take a look at these two. Since they're both in the countable range, I'm going to go ahead and average them, keeping in mind the original dilution factor though. So let's say 241, but that was a 10 to the negative 2 dilution. So I'm going to account back and do 10 to the 2. However, I'm going to average that with 35 times 10 to the negative 3 divided by 2. However, if you look, volume plated was 0.1. So that in itself is a 1 to 10 dilution. So you want to account for that. And by the way you can do that is just multiplying it by 10 at the very beginning. And that results in a final count of 2.95 times 10 to the 5th CFU per milliliter. And then our final problem here is another serial dilution problem. However, this one looks slightly different. Here, as you can see, the different dilutions are at different quantities, different ratios. So there's a lot going on in this problem. And whenever students see problems like this, it is very common for them to get overwhelmed. The trick is work step by step. So for example, here I can just choose one way or the other to go. I'll go ahead and go left to right. So I see that I have a sample, and I'm taking 1 milliliter of my original sample into 9 milliliters of diluent. So then I know, I'm like, okay, this here is a 1 to 10 dilution. Then from here to here, I'm taking 0.5 milliliters to 4.5 milliliters. That is, although it looks different, is still, at the end of the day, a 1 to 10 dilution. Here, I am taking 3 milliliters and having a, this was also not a good way to write it. I should have done like 0.5 milliliters plus 4.5 for a total of 5 milliliters. So here, 3 milliliters plus 27 gives you a total of 30 milliliters. This also is just another 1 to 10 dilution. Then here we are taking 1 milliliter and having 99 milliliters of diluent. So here, this one is different. It's actually a 1 to 100 dilution. Moving on, we have 1 milliliter, add 9 milliliters of diluent is a 1 to 10. Here we have 2 milliliters added to 18 of diluent is 2 to 20, which is also just another 1 to 10. Now here, this looks a little different. A lot of people sometimes forget to add this, but it's also a dilution. So here, 0.01 milliliters were plated. You could see this as a 1 to 100. You can just go ahead and multiply your final product by 100 to basically counteract this one. So the way now we put all of this together is, you see it says 84 colonies counted on the plate. So now we're working backwards, right to left. So we have 84 colonies, and we want to multiply that by 100, by 10, by 10, by 100, by 10, by 10, and by 10. And here I just went ahead and counted all of these. So you can also just go ahead and do the zeros route. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So we know this is also just 84 times 10 to the 9th. However, that's not in scientific notation. So turning that into scientific notation would be 8.4 times 10 to the 10. Yet again, CFU per milliliter, or colony forming units per milliliter. And that would go ahead and result our little tutorial on your most commonly seen medical math problems. Really, at the end of the day, it just results in you getting as much practice as possible. The more problems you do, the sooner you realize that these are actually very simple at their core. It's just a matter of getting used to doing the problems and being able to identify when you would do what. Thank you, and have a good day.